everyone! Welcome to part 2 of chapter 6. Last time we learned all about how to draw Lewis structures of molecules using the valence electrons of individual atoms that were contained in those molecules. Now we're going to learn how to use those Lewis structures to predict the shapes of our molecules. And we'll use those molecule shapes to determine whether our molecule is polar or nonpolar, which is going to allow us to predict a lot of properties of these molecules. So before you watch today's lecture, make sure you are super solid on drawing Lewis structures. So if you're still a little bit shaky, I would go and review it and do some practice problems before you begin. We will review Lewis structures a little bit in this lecture, but you're going to need to know the basics in order to kind of keep going. All right, let's go ahead and start. So the focus of today's lecture is really on VSEPR theory. VSEPR theory stands for valence shell electron pair repulsion theory. And essentially, this theory kind of helps us predict the shape of our molecules based on the electrons that are around our central atom. So if you'll recall, electrons are negatively charged. And if a negatively charged pair of electrons comes into contact or comes close to another negatively charged pair of electrons, then they'll repel each other because they're both negative. And so this is what's happening in our molecule. There are electrons in the bonds and also electrons in the lone pairs. So they will repel each other and they will orient themselves around the molecule to give them essentially the most space possible. Okay, so that's what this is saying down here. When it says molecules adopt geometries to minimize the electrostatic repulsion, essentially it's trying to, kind of satisfy all of the electrons and orient them all as far away from all of the other electrons as possible. Okay, and when they do that, that gives our molecule specific geometries. So in VSEPR theory, we will get a three-dimensional shape of our molecule. Remember, even though we draw these Lewis structures flat on our paper, these molecules are actually three-dimensional. And when you use our modeling system, you're going to be able to see that three-dimensional geometry. So in order to determine our shape, though, we're going to first need to draw the Lewis structure. So that's what I was saying earlier. If you're still a bit shaky on Lewis structures, you might want to review that before today's lecture. But after we draw the Lewis structure, then we're going to count the number of electron groups. This includes bonds and lone pairs. So we're trying to just figure out how many areas of electrons there are around the central atom. For this, we don't really care what's happening on the peripheral atoms on the edges. We don't really care about those. We're really just looking at the central atom. And then, like I said, because electrons are all negatively charged, we're going to orient those electron groups as far apart as possible around the central atom. So like in this first one here, linear, you can see that these are at 180 degrees away from each other. Like the electrons in this bond couldn't be farther away from the electrons in this bond. They're as far away as possible. So down here shows all of the different types of geometries we are going to learn about in today's lecture. Linear, bent, trigonal planar, trigonal pyramidal, and tetrahedral. There are more geometries that you'll learn if you take Chem 1 or later chemistry classes, but these are the ones that we are going to focus on in this class. All right, let's start with two electron groups. So if there are two areas of electrons around the central atom. So I want you to look at carbon dioxide. So carbon is our central atom, right? So we don't really care what's happening on our oxygens right now. We're really just looking at carbon. And so we want to see how many areas of electrons there are around carbon. So this double bond counts as one area. And this double bond counts as two areas, the second area. So there are two areas of electrons around this carbon. It doesn't matter if they're single bonds or double bonds or lone pairs. It doesn't matter at all. We're just looking purely at areas of electrons. So carbon dioxide has two electron groups, two double bonds, right? So this gives it what's called a linear electron group geometry, and it has a linear shape. As we move through this lecture, you're going to learn two different kind of types of shapes, essentially. The one on the left, when we go through these slides, is always going to deal with the total electron groups. Okay, so here we have 2 areas of electrons, so 2 electron groups, and that's what's giving us our linear shape, our linear electron group geometry. We will also have a linear shape. In this case, the electron group geometry and the shape have the same name, but that's not always going to be true. So I'll point that out as we go forward. The other thing I want you to know is that this has a bond angle of 180 degrees. Okay, so I want you to be able to recognize, okay, there's 2 areas of electrons around carbon, which is our central atom. That gives it a linear electron group geometry and a linear shape, and it has bond angles of 180 degrees. So you need to know electron group geometry, linear shape, and our bond angles. So here's some more examples. So remember, we're just looking at areas of electrons around the central atom for these linear groups. So 2 electron groups around the central atom. It doesn't matter what they are, but you need to have 2 groups of electrons. So like here is 1, 2, here is 1, 2, here's 1, 2. So in carbon dioxide, this top molecule, there were 2 different double bonds. Whereas HCN, we have a single bond and a triple bond. And in beryllium fluoride, we have 2 different single bonds. So it doesn't matter what the bonds are, right? It doesn't matter if they're single, double, or triple. We're just looking at areas of electrons. So if it has 2 areas of electrons, then it's always going to be a linear electron geometry, a linear shape, and a bond angles of 180 degrees. All right, so now let's look at what happens if there are 3 areas of electrons around our central atom. So here we go. Here's our central atom, right? That's carbon. And we have 1, 2, 3 areas of electrons around our central atom. This will give us trigonal planar electron group geometry. And it's also going to give us a trigonal planar shape. Okay, so here we still have the electron group geometry and the shape having the same name. The bond angles here are 120 degrees. So in linear, remember they were 180, and here they are 120. So again, remember, you need to remember the electron group geometry, the shape, and the bond angle. And this is with 3 electron groups around the central atom. All right, there's another way that we can have 3 electron groups around the central atom. So if you look at this one that we were just looking at, all of these 1, 2, 3, these are all bonds, right? Even though they're single bonds versus double bonds, they're all bonds. Whereas here in this one, this is sulfur dioxide, you can see in this molecule, we still have 3 areas of electrons, 1, 2, 3, but now one of the areas of electrons is a lone pair. This does not change the electron group geometry. Since it has 3 areas of electrons, it's still trigonal planar electron group geometry. So the electron group geometry is just counting up how many areas of electrons there are. If there's 2, it's linear. If there's 3, it's trigonal planar. The thing that changes, though, is our shape. Our shape essentially ignores the lone pair. So this lone pair is causing these bonds to bend down, right? Because the electrons in that lone pair are kind of pushing those bonds away from it because they're repelling. However, when we look at the actual molecule, it looks like this. Because if we were to draw or to build this molecule with, our modeling kit, we don't build the lone pair. But the lone pair is still there. It's kind of an imaginary lone pair here. And it's still pushing these down, but we don't see it when we build the shape. So for that reason, this molecule is called bent. Okay, so this is a bent shape because of the lone pair. So again, our electron group geometry stayed the same because there's 3 areas of electrons in this example and in this one. Still 3 areas of electrons, but the shape changed. This is a trigonal planar shape because all of them are bonds. However, this is a bent shape because one of those bonds now turned into a lone pair. Okay, the bond angle stays the same. It's still 120 degrees, whether it's a lone pair here or it's a bond. okay, because there's still 3 areas of electrons. All right, now let's look at what happens if there are 4 areas of electrons around the central atom. So here, carbon is our central atom, and we have 1, 2, 3, 4 areas of electrons around the central atom. This will give us a tetrahedral electron group geometry, and since all of those are bonds, the shape is the same name, okay? So it's also a tetrahedral shape. Our bond angles here are 109.5, okay? And this picture is wrong. This picture should say 109.5, my apologies, degrees, because those are the bond angles in a tetrahedral shape, okay? So just like we were looking at with the 3 areas of electrons where we turned 1 into a lone pair, we're going to do the same thing now. So instead of having 4 bonds, what happens if it's 3 bonds and a lone pair? It's still 4 areas of electrons, right? So that means the electron geometry is still tetrahedral because there are still 4 areas of electrons. The thing that changes, though, is the shape. This shape is called trigonal pyramidal, okay? And that's what this looks like. So you can see that it's not showing that lone pair, right? That lone pair is up there, and that's how those other 3 bonds got pushed down. But it's called trigonal pyramidal because it kind of looks like a triangular pyramid, okay? So that's why it's called that. Bond angles are still the same, 109.5, because that's based on the electron group geometry. The only thing that changed here was the name of the shape. So we looked at what happens if one of them is a lone pair, but what if we have 2 lone pairs? So in this case, this is water. We have 4 areas of electrons. 1, 2, 3, 4. That means it's still tetrahedral electron group geometry. But now 2 of those areas of electrons are lone pairs. So if we look at this, right, you can see that the lone pairs aren't being shown, but we're seeing those 2 bonds being bent down. So this is called a bent shape. Bond angles stay the same because remember, bond angles are based on our electron group geometry. The only thing that changed here was the name of the shape. This is a summary slide. I know that was a lot of information, and it takes a little bit to keep it all straight. So I have for you here the number of electron groups. So this is kind of backwards from what we learned. So 2 is down here. The first thing we learned was linear, right? If there are, 2 groups of electrons and none of them are lone pairs, then it's a linear electron geometry, a linear shape, and we have bond angles of 180. Okay? And so here are, if we have 3 different electron groups, they're both going to be called trigonal planar. Because remember, this electron group geometry, that name is just based on the number of areas of electrons. But if one of those areas is a lone pair, the name changes. And so now this one's called bent. But the bond angles are going to be 120 degrees, whether those 3 areas are have a lone pair or it's all bonds. And then if we have 4 areas of electrons, which are all of these up here, all of these are tetrahedral. Okay, because again, if there's 4 areas of electrons, their electron group geometry is called tetrahedral. If it has no lone pairs, then the name stays the same. But if one of them is a lone pair, we call it trigonal pyramidal. If 2 of them are lone pairs, we call it bent. Okay, and you've got some examples here down the side. No matter, if they're lone pairs or not, it's always going to be 109.5. Okay, on Canvas, I actually have a little reference sheet that talks about the different, it's essentially like this. It's a little bit easier to read, I think. But it has a table, and it's got the number of electron groups and their electron group geometry, the number of lone pairs on central atom. It's very similar to this, but it's a good reference sheet. So while you're working on, the practice problems or, your homework problems or even this lab that's coming up, I would recommend printing out that reference sheet and having it near you so that you can reference it as you're working. All right, let's get some practice on this. So If we were asked to determine the molecular shape for a given molecule, the very first thing we are always going to do is draw the Lewis structure. Okay, you cannot figure out the shape without drawing the Lewis structure. So don't try and cut corners, don't try and do this quickly. If I ask you for the shape, that means draw the Lewis structure and tell me the shape. Okay, so once we figure out the Lewis structure for a molecule, we are going to count the number of electron pairs, and I'm going to specify this on the central atom. Okay, very important. We don't care about the electron pairs on any other atoms, just the central atom. And we're going to arrange them to minimize electrostatic repulsion. Again, that just means kind of space them out as far apart from each other as possible because electrons are all negative and repel each other. The last thing, once we've done that, is to figure out the molecular geometry. And so the molecular geometry, when you hear that, that's the same thing as saying the shape. Okay, you'll hear me say molecular shape, molecular geometry, things like that. That's different from the electron group geometry. I know that's a little bit confusing. There's nothing I can do about it. But the molecular geometry is the same thing as saying the shape of the molecule. And again, that's going to result from only the bonding electrons. Okay, so let's try this out. So this says, use Vesper theory to predict the shape of silicon tetrachloride. First thing we need to do is draw the Lewis structure. So if you'll remember from the Honk rule, that will help us figure out which atom is the central atom. Chlorine is a halogen, which means it can only make one bond. Silicon is in the same group as carbon, and silicon can make 4 bonds. So that means silicon will go in the middle because it can make the most bonds. So we'll put silicon and then my 4 chlorines around the outside. Then we need to figure out how many electrons we can use in our structure. So silicon has 4 plus 4 times 7 from each of the chlorines, okay? And that will get us 32. So we can use 32 electrons in our structure. So we go 2, 4, 6, 8, and I'm going to go 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. All right, so we take a look and we see, did we use all of our electrons? Yes. And do all of the atoms have an octet? Yes. So that means we've drawn a good Lewis structure and we're ready to determine the shape. When we look at this, do you see that there are 4 areas of electrons around the central atom? 1, 2, 3, 4. So if it has 4 areas of electrons, that means that our electron geometry is tetrahedral. Okay, because anytime there are 4 areas of electrons, that means it's going to be tetrahedral. It doesn't matter if those areas of electrons are bonds, single bonds, double bonds, lone pairs, doesn't matter. There are 4 areas of electrons, so our electron geometry is tetrahedral. Since all of those areas of electrons are bonds, that means our molecular shape has the same name as our electron geometry. So it's also tetrahedral shape. Okay, so again, if all of the areas of electrons are bonds, then the name of our electron geometry and our shape are the same. If I had asked you for the bond angles, you would see that the bond angles for anything that's tetrahedral are 109.5 degrees. And it's good to start memorizing that. In general, I would recommend doing a lot of practice problems for these, but also making flashcards to help you memorize, okay, if it has this many areas of electrons and this many of them are lone pairs, what kind of shape is that and what are the bond angles? Flashcards will definitely help you memorize these for upcoming quizzes and tests. All right, let's try another one. What is the molecular geometry for formaldehyde? CH2O. Okay, so remember the Honk rule? So carbon can make the most bonds out of all of those, so carbon will go in the middle. Okay, and then we're going to space the other ones around the outside. Then we figure out how many electrons we have to use in our structure. We have 4 from our carbon, plus 2 hydrogens with 1 each, plus 6 from our oxygen. That will give us 12 electrons that we can use in this molecule. So we go 2, 4, 6, 8, 10, 12. Okay? So, but if you look at this, and you think, what's wrong? We've used all of the electrons, but as you can see, carbon doesn't have an octet. Carbon only has 6 electrons around it right now from those 3 bonds. So instead of all of those lone pairs being on oxygen, it needs to share one of those lone pairs and instead make a double bond with the carbon. So really, our molecule will look like this. Alrighty, so not like that. So now that we've figured out the Lewis structure for our molecule, we can go about determining the shape. Whoop. Sorry about that. I'll draw it again here. All right. Do you see that we have 3 areas of electrons? 1, 2, 3 around our central atom. That's telling us that we have a trigonal planar electron geometry. Okay, remember, anytime we have 3 areas of electrons, that's always going to be a trigonal planar geometry. Since all of those areas of electrons are bonds, then the name of our electron geometry and our molecular shape are the same. This is also trigonal planar. Okay, and if I had asked you for the bond angles, you would remember that anything that has an electron geometry of trigonal planar is going to have bond angles of 120 degrees. All right, I want you to try this one. What is the molecular geometry for phosphorus trihydride? Go ahead and pause here, try this problem out, and come back when you're ready to see the answer. Alrighty, the first step is to draw the Lewis structure for the molecule. So we have phosphorus and we have 3 hydrogens. Phosphorus will go in the middle because hydrogen can never go in the middle. So when we add up our valence electrons, we're getting 5 from the phosphorus plus 3 hydrogens with 1 each. So that gives us 8 total valence electrons that we can use. 2, 4, 6, 8. And that's the only way to draw it because remember, hydrogen follows the duet rule, and so it only makes 1 bond. Once we draw the Lewis structure for the molecule, then we can figure out its shape. So if we look at the areas of electrons, we have 1, 2, 3, 4 areas of electrons. So that means that our electron geometry is tetrahedral. However, do you see that not all of those areas are bonds? Up here, we have a lone pair. So that means that our electron geometry and our shape are not the same. Okay, so we need to figure out what is the shape that corresponds to 3 bonds and a lone pair. That shape is called trigonal pyramidal. Okay, and again, I would recommend some flashcards to help you memorize that, but for now, if you find that reference sheet, that'll definitely help you out. If it had asked for the bond angles, these would be 109.5 degrees because there are 4 areas of electron around the central atom. Remember, the degrees correspond to the electron geometry, not to the shape. Let's try another one. Go ahead, pause here, try this one out, and then come back when you're ready to see the answer. Alrighty, so this says, what is the molecular geometry for CS2? The first thing we need to do is draw the Lewis structure. So if we think about the honk rule, carbon can make 4 bonds, so we'll pick that one. Just for your reference, oxygen and sulfur kind of go together, so sulfur can only make 2 bonds, so that's why it's not going in the middle. So we put carbon and we've got 2 sulfurs. So now we add up our valence electrons, so we have 4 from carbon plus 2 sulfurs with 6 each, so that will give us 16 total electrons to use in our structure. So we go 2, 4, 6, 8, 10, 12, 14, 16. But as you can see, if I did it that way, now carbon doesn't have an octet, and so we're going to share some electrons with our carbon. Hopefully you can see that carbon only has 4 electrons right now, so it needs to share 4 more. So it's going to share one pair from each of these sulfurs. And that will get it to have 8 valence electrons. So really, this molecule looks like this. So now we need to figure out, okay, how many areas of electrons are around the central atom? So even though these are double bonds, they just count as one area of electrons. So that's one area, that's 2. Okay, so this means that it has a linear electron geometry because it only has 2 areas of electrons around the central atom. Because both of those areas are bonds, our electron geometry and our molecular geometry are the same. So it's also linear. And again, had I asked you for the bond angles, this would be 180 degrees for our bond angles because that corresponds to a linear electron group geometry. Alrighty, now I want you to get some practice. And really do make sure you practice and get really good at this because you're going to need it as we move forward in this lecture. So go ahead and complete problem number 3 on the Chapter 6 lecture worksheet. Once you're done, come back and we'll keep going. Alrighty, so we've been looking at how the electrons are arranged around the central atom, which is really helpful in determining the shape of our molecules. And that can tell us a lot about the properties of our molecule. But it's also important to understand how the electrons are being shared in these bonds. Remember that these molecules that we're talking about right now are made up of all covalent bonds. And in covalent bonds, those electrons are being shared. But just because they're being shared doesn't mean they're being shared equally. Think about it as, an older kid sharing a candy bar with a toddler. They may not break that candy bar directly in half if they were being told to share, right? They might just kind of give them a little square, or maybe they do half and half, right? But it's kind of the same with atoms. They don't necessarily share those electrons equally. Sometimes they do, but sometimes they don't. And this will give us different types of bonds. So let's go ahead and look at that. The way we can determine whether or not these atoms share the electrons equally is by looking at their electronegativity. So this is another periodic trend that we haven't covered so far. It actually follows the same trend as electron affinity. So if you remember electron affinity, it was increasing going up and to the right, which is going to be the same direction that we see increasing electronegativity. So electronegativity is the ability of an atom to attract electrons in a bond. Okay, so electron affinity was the ability to gain electrons. Electronegativity is the ability to attract electrons in a bond. So for one of them, right, electron affinity, we're talking about unbonded atoms, and here we're talking about bonded atoms. So that's the difference, but they do sound pretty similar. So when we talk about things that have a high electronegativity, the higher it is, the stronger the atom attracts electrons in a covalent bond. That means atoms with a really high electronegativity are going to shift the electrons toward them in the bond, and they're not going to share them equally. So our most electronegative atom is fluorine. Okay, and that's really important to remember. So if you can make yourself a note of that, fluorine is the most electronegative atom. We actually won't talk about these noble gases in terms of electronegativity because they already have 8 valence electrons and they're not going to form compounds. So we're not going to talk about their bonding properties because they're not going to make bonds. So instead, fluorine is our most electronegative atom on the periodic table. So there is a scale of relative electronegativities, and the most electronegative atom, which is fluorine, is assigned a value of 4.0. All of the rest of them have a value that's lower than that. So thus far, we've classified bonds as either ionic or covalent, right? They either transferred electrons or shared electrons. And so this is kind of a big extreme, right? If we think about sodium and chlorine, sodium is a metal and completely loses its electron to form a cation. whereas chlorine is a nonmetal and completely gains an electron to form an anion. Whereas if we had something like hydrogen bonded together like this, those two hydrogens, because they're the same atom, are going to share those electrons equally. But what happens when we get different atoms, like hydrogen and chlorine? Well, now, if we have two different atoms, they're not going to share the electrons equally. They are going to share them because they're both nonmetals, but they're not going to share them equally. Okay, chlorine is actually more electronegative than hydrogen, and so the electrons in this bond will actually sit closer to chlorine than they will to hydrogen. So we call this polar covalent. Okay, for these are covalent molecules that don't share electrons equally. If we had ionic, they're transferred. If we had purely covalent, they're completely shared. But if they're different atoms, then they are likely going to be polar covalent, which means they are not sharing them equally. Okay? So our bond polarity is going to be determined by the difference in the electronegativity of the two atoms that are sharing electrons. So that means you're going to need to have a table of electronegativities handy in order to figure out the difference between them. Okay? I have posted a reference table, a table of electronegativities, so you'll be able to determine the electronegativity value of the different atoms. I want to be super clear, this is not something you're going to need to memorize. I will always have that table available to you if I'm asking you a question about polarity. Okay, you're going to need to be able to calculate the difference between those electronegativity values and tell me if something is polar or not. Okay, if we have a difference in electronegativities that's 0 to 0.4, so that's a very small difference in electronegativities, then this bond is called nonpolar, and that says the electrons are shared equally. Even if it's not quite equal, they're shared pretty equally, so we call that nonpolar. So the way we're getting this difference is we're just subtracting the electronegativity values of the two atoms and figuring out what we get. And if it falls in this range, that difference, then that means it's nonpolar. However, if we get a larger difference in electronegativities, so 0.5 to 1.9, then those electrons are not being shared equally in that bond, and the electrons are going to sit closer to one atom than the other. This is called polar covalent, or oftentimes we'll just call it polar. Okay, so the electrons are not being shared equally in a polar bond, but they are shared equally in a nonpolar bond. And then if we get an electronegativity difference that's greater than 2, then we call it ionic. That's where the electrons can't be shared anymore because the difference in electronegativities of these two atoms is too big. And so instead of sharing them, they're actually going to transfer them. So it's all based on this whole difference in electronegativities. So let's do some examples. If we have a nonpolar covalent bond, or a lot of times we'll just say a nonpolar bond, this is going to have an almost equal or exactly equal sharing of electrons. This will have a very, very small difference in electronegativities, so like 0 to 0.4. So for example, if the atoms are identical, that means then both of those atoms have the same electronegativity value, which will give us a difference of 0, which will make a nonpolar bond. If you saw two nitrogen atoms bonded together, I will tell you, you don't need to bother calculating the difference in electronegativities. Since they're the same atom, one is not more electronegative than the other, so they're just going to share those electrons equally. So you really don't need to go through that whole process if you see that the atoms are identical. However, when you have something like this, where our atoms are different, then you're going to want to calculate the difference in electronegativities. So you just do big minus small. You don't need to do one or the other, just big minus small. And you can see our difference here is 0.2. So they have a very small difference in electronegativities, but it's small enough that it's classified as nonpolar. Okay, remember, we top out at 0.4 for nonpolar. So if they have a greater difference in electronegativities, then we call it a polar covalent bond, or sometimes we'll just call it a polar bond. And this will be an unequal sharing of electrons. This is where one atom is more electronegative than the other and is going to shift those electrons toward it in the bond. We'll see this when we have an electronegativity difference of 0.5 to 1.9. So if you see different atoms, like I was saying on the last slide, if you see different atoms, you're going to need to calculate the difference in electronegativities. So like here, oxygen and chlorine, they have an electronegativity difference of 0.5. It's the bottom end of this range, but it's definitely polar. Same thing with carbon and chlorine, or nitrogen and hydrogen. All of those are falling in this range, which makes them polar bonds, or polar covalent bonds. All right, I want you to give this a go. Which of the following would have a polar covalent bond? Okay, so go ahead, pause here, find that table of electronegativities that I was talking about in Canvas, grab that, and then calculate the electronegativity differences when you need to, and tell me which of these would have a polar bond. And then come back when you're ready to see the answer. All right, so to determine which one would have a polar covalent bond, we need to calculate the electronegativity differences between these atoms. So if we look at beryllium and fluorine, their difference is 2.5. This is one that people commonly mistake for polar because they just see a really large electronegativity difference. But remember, anything that's greater than 2 or 2 and greater is going to be an ionic bond. Also, you can recognize that beryllium is a metal and fluorine is a nonmetal. So that's going to be an ionic bond. So make sure that you're still trying to figure out, okay, is this ionic or is it covalent? Because if it's ionic, you don't need to bother calculating the electronegativity difference. You can just call it ionic because it's a metal and a nonmetal. So we only need to do this whole calculating the electronegativity difference if they're both nonmetal and they're both different atoms. So hydrogen and chlorine have a decent electronegativity difference here. That's 0.9. That falls in that range of polar covalent, and that's why that's our answer. Sodium and oxygen are a metal and a nonmetal again, so again, that's going to be ionic, but we're seeing that with this 2.6 electronegativity difference anyway. And then for the two fluorines, we didn't really need to calculate the difference in electronegativities because they're the same atom. So that's going to form a non-polar bond. That's where we see that 0. So the only one here that forms a polar bond is hydrogen and chlorine. All right, I want you to go ahead and try this problem. So I have 3 different types of bonds, or 3 different bonds there, and I want you to tell me which type of bond will form. Will it be a non-polar covalent? Will it be a polar covalent? Or will it be an ionic bond? So go ahead, pause here, try that out, and then come back when you're ready to see the answer. Alrighty, so again, to determine what type of bond is being formed, we're going to need to calculate the difference in electronegativities. So silicon to sulfur, that will be a difference of 0.7, and so that will be a polar bond. Cesium and chlorine, again, you didn't need to calculate the difference in electronegativity here. You could have just seen, okay, it's a metal and a nonmetal, therefore it's ionic. Okay, but if you calculated it, you would see that it's greater than 2, and therefore it's an ionic bond. And then silicon and phosphorus have very similar electronegativities. So similar, in fact, that they fall in the range of a nonpolar bond. Alrighty, so like I told you before, if we have a nonpolar bond, like this one, this is nonpolar, those electrons are being shared exactly equally between the 2 hydrogens. So that's why we're seeing those electrons sitting right in the middle of that molecule. However, if we have something like hydrogen and chlorine, chlorine is more electronegative than hydrogen is. And so what happens is chlorine pulls those electrons closer to the chlorine because it's more electronegative. When chlorine pulls the electrons closer to it, it kind of acts like it gained electrons. Not really, right? This isn't an ionic bond, so it's not really gaining the electrons, but since it's pulling those electrons toward it, it kind of thinks that it gained electrons, which means it's sort of negative, right? It's not completely negative. It didn't really gain them, but it's sort of negative because it kind of gains them by pulling them that direction in the bond. So that's where we're seeing this here. That weird little symbol is the Greek lowercase letter delta, and it means partial. Okay? And so that's saying that it's partially negative. So it's kind of negative, right? And we see the same thing over here with hydrogen. Since those electrons are shifting toward the chlorine in that bond, hydrogen kind of acts like it lost electrons. Not really, right? They didn't get transferred, but since they're sitting closer to chlorine, it kind of lost electrons. So that's why we're seeing a partial positive charge on hydrogen because it kind of lost them, and the partial negative on chlorine because it kind of gained them. So anytime we have a polar bond, we can do these partial charges. The one that is more electronegative, which is chlorine here, will get the partial negative, and the one that's less electronegative will get the partial positive. So like this here. So again, we have hydrogen and chlorine. Remember, chlorine is more electronegative than hydrogen. So what happens is those electrons in the bond sit closer to chlorine than they do to hydrogen. So when that happens, chlorine kind of acts like it gained electron, so it gets a partial negative charge. Not a full negative, but a partial negative. And hydrogen kind of lost electrons, so it gets a partial positive charge. So again, this is going to happen anytime we have a polar bond. So when we can draw these two different, this partial positive and partial negative for these polar bonds, we can draw this arrow that kind of tells us in which direction the electrons are going to shift. So let's take this example here. Carbon versus oxygen. If we were to calculate the electronegativity difference of those two atoms, you would see that this is a polar bond. Anytime we have a polar bond, we can draw our partial charges. Since oxygen is the more electronegative atom, the partial negative goes on oxygen. Since carbon is less electronegative, it gets the partial positive. Once we do that, then we can draw these arrows that you see down at the bottom. The arrows are always going to go in the direction of the bond, right? They're going to kind of line up with the bond, and they're always going to point to the more electronegative atom. So the way I like to do this is I put a plus sign by the positive one and finish the arrow toward the negative one. Same thing here. I put a plus sign by the positive one and finish the arrow toward the negative one. So that's always going to show the direction that the electrons are being shifted in that bond. So here they're all shifting to the right just because that's the way I've drawn it, but it doesn't have to go to the right. It's just always going to point to the more electronegative atom. So these arrows that we're drawing, these are called dipoles. They are indicating that these polar bonds have a separation of charges, that one of the atoms becomes partial negative and the other one becomes partial positive. So those are called dipoles. So if you hear me talk about dipoles, I'm talking about these arrows that we can draw. All right, let's go ahead and practice this. Complete problems number 4 to 7 on the Chapter 6 lecture worksheet. Once you're done, come back and we'll keep going. Alrighty, so now we've talked about polar and nonpolar bonds, and we've also talked about drawing dipoles. We can use all of that information and our ability to draw Lewis structures to determine whether molecules are polar or nonpolar. So again, we were just talking about whether bonds are polar or nonpolar, and now we're going to use that to talk about whether entire molecules are polar or nonpolar. So if we have a nonpolar molecule, one of the ways that we can get that is to have all of the bonds be nonpolar. Okay, so like here, if we have two hydrogens, we're not going to calculate our difference in electronegativities because they're both hydrogen. They have the same electronegativity value, so their difference is 0, which means those electrons are going to sit directly between those hydrogens. Same thing for the chlorine, right? The electrons are going to sit directly between the chlorines. So these are both nonpolar molecules because they contain nonpolar bonds. It's the same thing here. Our carbon and our hydrogens have very similar electronegativities. So if you were to calculate the difference, that would fall in that range for a nonpolar bond. So all of these bonds here are all nonpolar. So that makes our entire molecule nonpolar because it only contains nonpolar bonds. We can also get nonpolar molecules a different way. This is when we have all of our dipoles cancel each other. Okay, they all cancel out because we have a symmetrical arrangement around our molecule. So two examples that we're going to look at are carbon dioxide and carbon tetrachloride. So carbon dioxide looks like this. Okay, the carbon-oxygen bonds are polar. So when they're polar, we need to draw our dipoles. Okay, oxygen is more electronegative than carbon. So that means the partial negatives are going to go on oxygen. Oops, that's a negative, my apologies. Actually, let me rewrite that just so we don't think it's positive. There you go, partial negative. And then the partial positive will go on the carbon. Okay, so for each one of these bonds, I can draw a dipole. Remember, draw a plus sign at the positive one and point to the negative one. Draw a plus sign at the positive one and point to the negative one. Do you see that these two dipoles are going in exactly opposite directions? When they go in exactly opposite directions like this, like one is going left and the other one is going right, these dipoles are actually going to cancel each other out, which makes this entire molecule nonpolar because all of the dipoles canceled out. We can think about the same thing with carbon tetrachloride. Carbon tetrachloride looks like this. All right, there's carbon tetrachloride. If we were to look at our table of electronegativities, we would see that chlorine is more electronegative than carbon. So that means that chlorine is going to get our partial negatives, and carbon will get our partial positives. So for each one of these bonds, we are going to draw a dipole. All of these dipoles will start at carbon and point to chlorine because we put a plus sign at our positive one and finish it toward the negative one. All right, I know this is starting to look a little bit messy, but do you see that we have one dipole going to the left and then one dipole going to the right? Those two dipoles cancel each other out. We also have one dipole going up and one dipole going down. Those two dipoles are exactly opposite and they cancel each other out. So in carbon tetrachloride, all of the dipoles canceled out, which makes this a nonpolar molecule. So if all of the dipoles cancel each other out because they are arranged symmetrically like in these ones, that means that this is a nonpolar molecule. All right, so if we have dipoles that don't all cancel out, then we are going to get polar molecules, okay? So in order to do this, and in order to determine whether any molecule is polar or nonpolar, you are always going to have to draw the Lewis structure. That's going to be the first step. And so like I was saying earlier, if you're not good at Lewis structures, make sure to get good at them really fast because that's one of those fundamental skills that we're going to use a lot in this course. So again, step one, draw the Lewis structure of our molecule. And then figure out whether the bonds within it are polar or nonpolar. If the bonds are polar, then you're going to draw a dipole for each polar bond. Then we're going to see if the dipoles cancel out. If all of the dipoles cancel out, then it's nonpolar. But if we have at least one dipole that doesn't cancel, that makes it polar. That makes the entire molecule polar. And usually that is going to happen when we have a lone pair on the central atom. So that's going to be like my pro tip to you. If you have a lone pair on the central atom, your dipoles won't cancel out. And we're going to look at that in just a minute. But sometimes they will if you don't have lone pairs. But if you have lone pairs, then they're for sure not canceling out. Okay? And that's what this is talking about here. So let's look at this. So if we have a molecule like HCl, hydrochloric acid. So it's a really simple molecule. It's linear and it looks like this. It has hydrogen and chlorine, and then there's my little lone pairs around my chlorine. In this bond, if we look at it, we can tell that it's a polar bond because it has a large difference in electronegativities. Since chlorine is the more electronegative atom, that one will get the partial negative charge and hydrogen will get the partial positive. So when we draw this dipole, we're going to put a plus sign at the positive one and finish it toward the negative. So we can only draw one dipole for this molecule because there's only one bond, right? So in this case, there's no way it can cancel out because there's only one bond here. So that makes HCl a polar molecule because we can't cancel out that dipole. Let's try another one. Let's try water. Water is H2O. And when I was talking to you guys during our Lewis structures molecule, I said that we needed to draw water a very specific way. And I told you we needed to draw water in this bent shape, right? I told you we had to draw water like this, okay? And today's lecture talks about why. So first let's go through how we do it correctly, and then I'll show you why we don't do it incorrectly. So in looking at this, if we look at the bonds, the oxygen-hydrogen bonds, those are polar bonds because it's a large difference in electronegativities. So we put the partial negative on oxygen because it's the more electronegative atom. And we'll put the partial positives on hydrogen. For each one of these bonds, we can draw a dipole. So start at the positive, finish it toward the negative, start at the positive, finish it toward the negative. Okay? Do you see that we do have two bonds, but they're not equal and opposite? One of them is going up and the other one is going left. They are not going in opposite directions. To cancel out the one that's going up, we would need one going down. To cancel out the one going left, we would need one going right. So these are not canceling out, therefore this molecule is polar. Okay, and I was really specific that you needed to draw water in this bent shape. And hopefully that makes more sense now after talking about our VSEPR theory, right? Here we have 4 areas of electrons. 1, 2, 3, 4, which gives this tetrahedral electron geometry, but our molecular shape, because it has 2 bonds and 2 lone pairs, that shape is called bent. So as you can see, I've drawn my water in a bent shape to kind of mirror what we know its shape actually is. So let's say you had drawn it incorrectly. Let's say you drew water like this, even though I told you not to 1,000,000 times. All right, so there's water. So let's, again, go through this whole exercise. Partial negative on oxygen and our partial positives on hydrogen. Doesn't matter how we draw these bonds will still be polar, right? So if they're polar, we need to draw our dipoles. So we'll put a plus sign at the positive one, finish our arrow, plus sign at the positive one, finish the arrow toward the negative one. So look here. If we had drawn this molecule incorrectly, do you see that one of these arrows is going to the right and the other one is going to the left? These look like they cancel out, right? And so a lot of people will get this question wrong if I talk about water because they'll draw the Lewis structure for water incorrectly. They'll draw it like this and they're like, yep, those totally cancel. One went left, one went right, therefore water is nonpolar. And honestly, guys, if water was nonpolar, there would be no life on Earth. The only reason there's life on Earth is because water is polar. So that's really, really, really important. We are going to get into this more when we talk about intermolecular forces, but just be really careful. When you're drawing these bent shapes, always make sure the 2 lone pairs go next to each other and the 2 bonding pairs go next to each other. Because if you draw it like this structure here on the right, you're going to think water is nonpolar, and it's definitely polar. Okay? Let's try some more. Let's try NH3. So NH3 looks like this. And we would need to figure out, is this polar or nonpolar? Well, all of these bonds are going to be polar because there's a large difference in electronegativities between nitrogen and hydrogen. So nitrogen gets the partial negative, and all of these hydrogens get a partial positive. So then we draw our dipoles. Again, start at the positive one and finish it toward the negative one. All right, so looking at this, do you see that two of our dipoles cancel out? This one and this one? They are going in exactly opposite directions, so they cancel. However, one of our dipoles doesn't cancel out. Therefore, this molecule is polar because we have a leftover dipole. Remember, if any dipoles don't cancel, then it's going to be polar. Like I said earlier, if you have lone pairs on your central atom, your molecule will always be polar because there's no way for your dipoles to cancel out. Okay, so that's just kind of like my pro tip to you. If there are lone pairs on your central atom, your molecule is going to be polar. All right, here's our last example, CH3F. So here's our molecule. Okay, we have two different types of bonds happening. We have a bond between carbon and hydrogen, and we also have a bond between carbon and fluorine. If we look up the electronegativity differences of carbon and hydrogen, you'll see that those are non-polar bonds. So for non-polar bonds, we do not draw dipoles. I'm going to say that again. If you have a non-polar bond, you do not draw a dipole. Okay, so carbon and hydrogen makes a non-polar bond, so we're not going to do anything with that. However, the carbon to fluorine bond is polar, so we're going to need to draw our dipole for that one. Fluorine is the most electronegative atom, so it's always going to get the partial negative, which leaves carbon with the partial positive. So then we can draw our dipole, start at the positive, finish it toward the negative. That is the only dipole in this entire molecule. Even though there are bonds going to carbon, from carbon to hydrogen, those are not polar, so we don't draw dipoles. So this dipole here that we've drawn has nothing to cancel out with because there are no other dipoles present in the molecule. Therefore, this molecule is polar because there's just the one dipole that can't cancel out. All right, I want you to try this one. Determine whether the molecule OF2 is polar or nonpolar. Okay, so the first step, is, before you can even draw it, I usually draw it first, but I would figure out whether these bonds are polar or nonpolar, right? And if the bonds are polar, then you can draw the Lewis structure. You can also do it the other way around. Doesn't matter, but you're going to need to do these in some order. So let's draw our Lewis structure. So OF2. If we draw our Lewis structure, it's going to look like this. Okay, this is one of them. Be very, very careful. Do you see that our central atom has two bonds and two lone pairs? Anytime you have two bonds and two lone pairs, you're going to remember, because you're going to memorize this, two bonds and two lone pairs makes a bench shape. So do not draw it linear like I was just talking about with water. You need to draw this as a bench shape. Once you've drawn it and you recognize that this bond is polar, even though it's just barely polar, it is polar. Okay, so then we'll go through and we will draw our dipoles. Fluorine gets our partial negative because it's the most electronegative atom, and oxygen will get our partial positive. Okay, then we're going to draw our dipoles, and we will see that our dipoles don't cancel out. There are two dipoles, but they are not equal and opposite, therefore they don't cancel out, making this molecule polar. Okay, but again, if you had drawn the Lewis structure wrong, you may have thought that this molecule was nonpolar. So be very, very careful when drawing Lewis structures. It's very important to draw them correctly. All right, I want you to try this one. Is carbon tetrachloride polar or nonpolar? Go ahead and try this, pause here, and then come back when you're ready to see the answer. All right, so let's go ahead and draw this. Okay, so carbon tetrachloride looks like this. All right, so all of those carbon-chlorine bonds are polar. Okay, so anytime they are polar, right, and again, we see that because we would take our difference in electronegativities and we would see which range it falls in. So since these are all polar, now we are going to, figure out our dipoles. So all of the chlorines are going to get a partial negative because chlorine is more electronegative than carbon is. Carbon will get the partial positive. So for each bond, we're going to draw a dipole. It's going to go from the carbon to the chlorine. All right, so once we've drawn that, we see, do my dipoles cancel out? We have one going left and one going right, those cancel. And then we have one going up and one going down. Those cancel. So here, all of our dipoles are canceling out, which means that this is nonpolar. And specifically, it's nonpolar due to our polar bonds being arranged symmetrically around our atom. The fact that they're arranged symmetrically is the reason that they all cancel out. So if you weren't sure how that kind of played into the explanation, that's the technical way of saying it, is that they are arranged symmetrically about the carbon atom. Okay, this is not true. This would have been what would happen is if all of those carbon-chlorine bonds were not polar. However, the carbon and chlorine bonds are polar, and the reason this molecule is nonpolar is because they all canceled out. Alrighty, that was a lot for today. I want you to go ahead and practice this by doing problem number 8 on the Chapter 6 lecture worksheet. And this actually wraps up our lecture for today. We've covered a lot of ground. We learned how to use our Lewis structures to determine the shapes of our molecules. And we talked about electron geometry. We also talked about molecular geometry, which I told you I will often call the shape. And then we also talked about the bond angles. Remember, you need to be able to draw Lewis structures and identify those 3 pieces of information. I recommend making some flashcards so you know, if it has this many bonds and this many lone pairs, then it's going to be this shape versus that shape. And it'll also help you with things like, the bond angles and such. After that, we learned about electronegativity and how electronegativity dictates how our atoms are sharing electrons in our bond. Are those atoms sharing the electrons equally, or are they not? And if they're not sharing them equally, then that's called a polar bond. If they are being shared equally, it's called a nonpolar bond. And then we also used that information about polar and nonpolar bonds to draw dipoles, which allowed us to figure out whether molecules were polar or nonpolar. This lecture is a lot of information. And the only way to really, really get good at it is to continually practice these skills. And they're skills. And you will get better at them as you do more and more practice. So make sure to do all of these recommended lecture worksheet problems. So keep working hard. And if you have any questions, send them my way because I'm more than happy to help you out. I like drawing Lewis structures. I think it's a lot of fun. And hopefully you do too. But if you have any trouble, please ask me and I'm more than happy to help. Otherwise, keep working hard, and I'll talk to you guys next time.